So I want to go over just a couple of things from before, because I think they need a little clarification, and then we'll continue. And then, of course, if you have any questions, you'll ask those as well. Okay, so I had two problems which I have right here. I want to remind you, firstly, we talked about discrete distributions, and there are a whole bunch of them. Now, if you look at the binomial, for example, the range of the binomial, the possible values could be 0, 1, 2, up until n. Let's suppose this is a binomial with parameters n and p. And the probability that x equals k turned out to be, sometimes I wrote it as b, k, and p, but usually you write it right out. It's pretty easy to get. It's p to the k, q to the n minus k. And then I talked about the Poisson distribution. Now, the values of k here could be infinite. They take discrete values, but they go on forever. And the probability mass function was defined to be lambda to the k, e to the minus lambda over k factorial. And I should remark, we showed for the binomial that expected value when x is equal to the number of occurrences is n times p, and its variance is n times p times q. And we proved that the variance and the expected value of the Poisson distribution were both the same, namely lambda. Now, I also showed the other day, when n is large, and it really doesn't have to be that large, and p is small, such that n times p is a constant, then the binomial could be approximated by the Poisson. And by the way, notice the following. In the binomial, e is equal to np. Well, if np is equal to lambda, that makes sense, so it's certainly consistent. And the variance is n times p times q. But if p is small, as I suggested, and n is large, 1 minus p is going to be close to 1. So then this approach is just n times p, which is again lambda. So in certain situations, when you have a binomial distribution, when n is large and p is small, it might be useful to, even though it's a binomial, it might be easier for you to do the computations using a Poisson distribution. And notice, of course, the number e, we all know what that is, and we know how to use it in our calculators. It's 2.718281828, and then it does a lot of weird things. Now, I want to illustrate this first remark with an example. Okay? So let's suppose, so here's an example, and let's suppose I have 80 misprints or typos are randomly distributed in a 400-page book. What's the probability a particular page has, say, two misprints and B at least 2? Okay, so We have 80 misprints that are randomly distributed in a 400-page book. Well, let me just firstly point out, this is clearly a binomial distribution. If I let X equal to the number of misprints per page, then the probability, since there are 400 pages, a misprint will appear on any page. By the way, you really got to be a little technical here. We got to assume that each page has about the same number of characters. So you're just likely, a misprint is just likely to be on any page than any other page. Then the probability a misprint will appear on any page, if there are 400 pages, is 1 out of 400. And the number of misprints we have is 80. So if we want to do this problem exactly using a binomial distribution, what's the probability that X equal to, say, 2? If this were a binomial distribution, this would be 80 choose 2. P, which is 1 over 400 to the 2 times 399 over 400. That's the complementary to the 78. And if you actually work this out, by the way, I think I did with my calculator yesterday, I get 0.1625. Now notice in this problem, n is large, 80, that's fairly large, p is small, and n times p together, which is 80 times 1 over 400, is what's that turn out to be? 0.2? 0.2. So let's suppose I use the Poisson approximation. Then the probability that X equals to 2 is lambda to the k, e to the minus lambda over k factorial. And if you work this out, by the way, you get 0.01637. How is that? Notice to 3 decimal places, they would agree. If I round this off to 3 decimal, I get 0.163, and that's exactly, here I get 0.164. So that's pretty close. And by the way, the second question, what's the probability that I get it has at least, what was the exact wording, 2 or more? At least 2 misprints? Well, I would do this one by complementation. Probably has none or 1. And this would just turn out to be 1 minus e to the minus 0.2, 0.2 to the 0 over 0 factorial plus e to the minus 2, 0.2 to the 1 over 1 factorial. And if you work this out, assuming I did it correctly, it gives you 0.01752. The answer isn't important here. It's the methodology that I really care about. So notice, by the way, if you think about a Poisson distribution, some people like to call it the distribution to use when the event occurring is rare. By rare, we say the probability of success is pretty small, P, whatever you call success. Just one other interesting example, which is not a binomial, but well, maybe you can, but you can think of it as directly as a Poisson. Suppose I give you the following information. 2% of airline ticket holders fail to make their flight. Whatever the reason, maybe they run late or whatever the reason is, let's suppose 2% fail to make their flight. So let's suppose an airline sells 105 tickets for a flight with 102 seats. How likely are they, meaning the airlines, to be overbooked? I'm sure all of you have already been to the airport on some busy days when you hear announcements saying if anybody wants to give up their ticket because the flight's been overbooked, they'll give you a free ticket anywhere in the country for a year or something like that. Because this happens. So the question is, how likely is this to happen? So let's let x equal to the number who missed the flight. If x is equal to 0, 1, or 2, right? Remember, there are 102 seats and there are 105 tickets. So as long as if x is equal to 0, 1, or 2, they overbook. Because remember, there are 105 tickets and 102 seats. So the difference is 3. So as long as less than 3 people miss their flight, they're going to be overbooked. So this is a Poisson distribution with n equal to the 105. The probability is 2%. So lambda, which is n times p, turns out to be 2.1. So we need to compute the probability that x equals 0 plus the probability x equals 1 plus the probability that x equals 2. By the way, I made up these numbers, so don't expect a great answer. And if we work this out, by the way, they all have this factor in it, so I'll just take it out. I get 1 plus 2.1 plus 2.1 squared over 2 factorial. And this turns out to be roughly 0.6496, or about 65% of the time this would happen, which means the airline would lose a lot of money if this were the case. Okay, I wanted to do these 2 examples for you. I thought it was important for you to see some applications of the Poisson distribution. I think all the other ones are very straightforward. And if there are problems, please let me know and we'll talk about it. Okay, so now I want to get to what I really think is the most important part of the course, continuous random variables. Up until now, we considered problems where the range of the random variable was discrete, meaning it took either a finite number, the range took or had a finite number of values, or could have had a countably infinite number of values. For example, if it's a binomial distribution, the range was, say, 0, 1, 2, up to n. If it were a Poisson distribution, it could be 0, 1, 2, forever. This could be infinite. Or I can have things like -2, -1, -0.5, 0, 1, 20. Here's a range of some random variable, but it's clearly discrete. Now, suppose we could have situations where the range can take on any value, for example, or any value within a certain limit. For example, suppose I tell you the life of a bulb, of a light bulb, is 2,500 hours. And let the random variable t equal time to failure. Notice t can be any number in the interval between 0 and 2,500. Or remember this notation, the closed interval. I can take on any value between 0 and 2500. Instead of having discrete values, we now have a continuum of values. So with this in mind, we will define a continuous random variable. I want to use the same notation I'm using in the book. Has a range which is an interval or a union of intervals. We'll see how that can happen as well. So let's talk a little bit more about this and let's get a feeling for what's happening. So it might be, for example, that I may have some random variable where its range consists of all real numbers from minus infinity to infinity. Or maybe I have one whose range goes from 0 to infinity. Or maybe I have a random variable, say x, whose range is the union of the interval, say from 0 to 10, or from 15 to 1,000. It's the range of the interval, that union. I mean, I can have lots of different possibilities. So now let me go back and reflect. So how do we define a probability in such a case? What happens here? So let me remind you, let's suppose I had some kind of distribution, a discrete distribution. And I had its histogram. Let's just say it takes on 4 values. And of course, if you remember when I did these histograms, I did it so that the width of each of these rectangles is 1. And let's suppose this is 0.2, this is 0.5, I'll make this 0.1, this is 0.3, I'll make this 0.4, 7, and this is 0.3, this is 0.2, okay. So notice, I actually give you the probability that each of these happening. In this histogram, the area of this rectangle represents the probability that x equals 1. I rigged it up so that the width times the height gives you the probability. And similarly, the width times the area of this parallelogram gives you the probability that x equals 2, and so on. So effectively, if I ask what's the probability that x is between 1 and 3, I just add up the areas, 0.3 times 1 plus 0.4 times 1 plus 0.2 times 1, and that would be 0.9. That would give me the probability. So you can think of a probability in the discrete case as being the area under these rectangular graphs, these histograms. Now what happens if, in fact, the range, say, goes from here to here, okay, say from A to B. Well, instead of, what may happen now is if we sort of plotted it, we may get some kind of continuous graph like so. I'll call this f of x. And if I wanted to know, say, what the probability is, suppose this is C and this is D, what the probability that x is between, say, C and D, I might say, hey, it's just that area, in analogy with the discrete case. And by the way, we know how to find areas under continuous curves or even piecewise continuous curves because we all took calculus. So the first thing we need to do is, how do we model all this? So here's what we do. So basically what this says, if you take this, what this area represents is sort of the probability that x will lie between C and D. So somehow it's some kind of f values multiplied by a width. Keep that in mind when we had the mean value theorem for integrals. So here's what I want to do. Clearly, this function, which is somehow going to represent a distribution of our probabilities clearly has to be a non-negative function. So I want to define this function f of x, and I'm going to call this function, by the way, the probability density function. Okay. And we all know that the sum of all the probabilities must always be 1. So the other requirement is that if I look at the total integral from minus infinity to infinity over the entire range, this integral must be 1. That's analogous to the statement the sum of all the probabilities is equal to 1 for a discrete random variable. And moreover, if I want to know what's the probability that x lies between, say, two numbers a and b, that would just represent, let's suppose this is my function now, and this is a and this is b. It would just be this area, which we all know from calculus is the integral from a to b of f of x dx. And by the way, sometimes instead of f of x dx, I might write, since it's a dummy integration variable, f of t dt. It doesn't make a difference. You can use any letter you like. So I've defined the following, and then we'll give an interpretation to it in a minute. The probability density function is, and we will just call that now a PDF. This is analogous to the probability mass function. Is some function f of x, which will always be non-negative. It has the property that if you integrate it over its entire range, the integral will be 1. And the probability that x lies between a and b will just be the area under the curve between a and b. Okay. A couple of observations. So let's suppose I want to interpret what the probability density function is. So let's look at the probability that x lies between, say, a minus a little bit and a plus a little bit. I'll call that e over 2. Well, according to my definition, this is equal to a minus e over 2 to a plus e over 2 f of x dx. Now, this interval is so small, so over this interval, this is essentially a constant. So if this is essentially a constant, then what constant will it be? It'll be f of a. So essentially I have f of a times the integral of 1 dx from a minus epsilon over 2 to a plus epsilon over 2. This gives me just f of a times epsilon. So that gives me an interpretation. So essentially, this is telling me that f of a is nothing more than the probability per unit length. If we now divide through, so we get the probability divided by this number. So in a sense, this is the probability per unit length over a small length. So we think of this as being a density. It's analogous to a mass density in physics. And that's why it's called the probability density function. A little bit more on this. So the probability that x is between a and b for a continuous random variable is given by this. Okay, what happens if I change b to a? Well, what do we know about an integral going from a to a? What's that integral going to be? What will that integral be? Or better yet, here's my graph, say from C to D, and let's suppose this is A. What's the area of a line? The area of a line is 0. So this says for a continuous random variable, the probability that x, the only way x can be less than or equal to a and smaller than or equal to a is if x equals a equals 0 for a continuous random variable. By the way, notice this is not the impossible event. For a discrete random variable, if the probability event was 0, that had to be the empty set, the impossible event. But here, the probability can be 0, and yet it's something that could happen. But it happens with low probability, with probability 0. By the way, that tells you the following. So the probability that x is less than or equal to a is the same thing as the probability that x equals a for a continuous random variable. I'm sorry, the probability, I said that wrong. Let me say it again. That is, it doesn't make a difference whether you're using quality or not here. So for example, this probability is the same as this probability, which is the same as this probability, including or excluding an endpoint, doesn't change the probability because the probability at a point is 0 because there's no extra area contributed under the curve. So let me give you a simple example. I take one from the text. Suppose I define my probability density function to be the following. It's equal to x if x is between 0 and 1, it's equal to 0 between 1 and 2. It's 1/2 between 2 and 3, and it's 0 elsewhere. So that means this looks something like this. Between 0 and 1, it's x. To the left of 1, it's 0. Between 1 and 2, it's 0. It's a half. By the way, when this is 1, this is 1. It's a half between 2 and 3. And afterwards, it's 0. So here's a graph of my density function. And by the way, notice the following. Okay, the height here is a half. Notice if we added the integral from -infinity to infinity of f of x dx, in this case, we all have to look at the integral from 0 to 3 because it's 0 everywhere else. And I don't even have to do any integration because notice this is a triangle. What's the area of this triangle? It's 1/2 the base times the height. Here's a rectangle. A rectangle is the base times the height, and this is equal to 1. So I have, in fact, this is a PDF, a probability density function, because the total area under the curve is 1. Let's change it a little bit, and let me show you, for simple curves, you actually don't even have to integrate. Suppose I tell you f of x is defined as follows. It's equal to a times x, if x is between 0 and 4, and it's equal to 0 elsewhere. Now, I don't have to draw a picture. I ask a couple of questions. Question number one is, what is A? And two, I ask you to find the probability that x is between 0 and 3. Okay. Well, I could actually do this by a picture. If x is between 0 and 4, it's linear. It looks like this. And this, when x is 4, the y value would be 4a. So I could say, okay, the total area on the, and 0 everywhere else. So the total area under this curve from minus infinity to infinity, in this case, I only have to worry about the area between 0 and 4 of f of x dx. Now I could integrate this, by the way. That would be, this would be ax dx. If I integrate this, I get ax squared over 2 from 0 to 4, which gives me 8a. But I know this must be 1, so a is 1/8. By the way, I could have done this more easily without using calculus. Notice the region is just a triangle. The area of the triangle is 1/2 the base times the height, which is 4a or 8a, and I want that area to be 1, gives me the same answer. Now the second question asks, what's the probability x is between 0 and 3? Well, that would just be the integral from 0 to 3. Now, ax, remember, this is now, what did a turn out? 1/8? Just 1/8 x dx. If I integrate this, this would give me x squared over 16 from 0 to 3, which is 9 over 16. I want to remark that I could have done this problem geometrically. If this is 3, then remember this, the graph is, what was it, 4a? I'm sorry, 1/8 a. So remember, we now showed that the equation of this line, f of x, is equal to 1/8 x. So this height must be 3/8. So this is a triangle. The area is 1/2 the base times the height, which gives me 9 over 16, which is what I got a minute ago. Okay, a little more. The next question I do, it's an important one to work out, is suppose I look at the following function. I define it to be e to the minus x for all x greater than 0, greater than or equal to, doesn't make a difference, and 0 elsewhere. This, in fact, is going to be called an exponential distribution with parameter 1. I'll talk about that a little later on. And the first question I ask is, what's the probability that x is greater than 1? Well, that would be the integral from 1 to infinity of e to the minus x dx. Now, I tell you how to handle integrals of this type on the video I did earlier this morning. Effectively speaking, what you do is you can keep the infinity as it is, being careful with it, or if you want, you can think of this problem instead. And when you're done, you let n go to infinity. Okay, so in either case, let's suppose I leave the infinity in there. The integral of e to the minus x is minus e to the minus x. And I want to evaluate that between 1 and infinity. So this would be minus e to the minus infinity minus 1. Now, if I treat the infinity like a number, or if I could, I can call it n if you like, and then let n go to infinity at the end, I get 1 over e to the infinity minus 1. Well, e to the infinity is infinity. What is 1 over infinity? What will this number approach? 0. So this would give me 1. Oh, something's wrong here. I'm sorry. I'm sorry. I made a mistake. E to the minus 1, right? Yes, e to the minus 1. So this gives me just e to the minus 1, which if you use a calculator, you can figure it out pretty easily. So here's a reverse question here. For the same problem, find A if the probability that x is less than A is 0.4. Well, the probability that x is less than A in this case is just the integral from 0 to A of e to the minus x dx, and we want this to be 0.4. If we integrate this, we get minus e to the minus x between 0 and a equal 0.4. So this gives me minus e to the minus a minus 1 equals 0.4, or minus e to the minus a plus 1 is equal to 0.4, or e to the minus a, let me just see what that gives me, minus 0.6 is 0.6. If I take logarithms of both sides, so I get minus a is equal to ln of 0.6. So a is equal to minus that. And that turns out to be somewhere or other 5108. Okay. So that was a variation. Remember what the CDF is. The CDF was defined to be the probability that x is less than or equal to x, and that was called the CDF, the cumulative distribution function. So for a continuous random variable, the probability is equal to the integral from minus infinity up until little x. I'll call it t this time, f of t dt. And notice some observations. Notice firstly, when x is infinity, we get the total area under the curve. And that's 1. Notice the other fact that when it's minus infinity, well, we're not really doing any integration. We haven't gone anywhere. We haven't generated any area. This will be 0. And the other thing is to remember from calculus, the derivative of an integral is the function you started with. So the derivative of the CDF is equal to the PDF. That's an interesting result in its own. Now, also observe the following. The probability, we showed, well, and by the way, notice I could have written this instead, or I could have put in I could have written this. For continuous random variable, it doesn't make a difference. Or all of these cases are the same. So I claim the following result. This is nothing more than the fundamental theorem of integral calculus, but we can show you with respect to probability. Why is this the case? Let's suppose this is my PDF. So f of b would represent this entire area. F of a would represent this area in red. So if I subtract the entire black area, the red area from the entire black area, I'm left with this area right here. See it? But that's just the probability. That area is the probability that x lies between A and B. So it's pretty easy to get the CDF. If you look at the example we did a minute ago, suppose f of x is equal to, what was it, 1/8 x between 0 and 4, and 0 elsewhere. So if I want to get, so notice our graph looks like this. So f of x accumulates no area for all x less than 0. If x is between 0 and 4, then the area I have now is I get the integral from 0 to x of 1/8, I'll call it t instead of x now, dt, if x is any number between 0 and 4. And at 4, we get the entire area under the curve, which is 1. So let me rewrite this. So if I do this integral, what do I get? I get t squared over 16 from 0 to x. So that gives me x squared over 16 if x is between 0 and 4, and it's 1 when x is greater than or equal to 4. So there's my cumulative distribution function. By the way, notice the following. For a discrete random variable, the probability that a less than x less than or equal to b, if you remember this result, this was f of b minus f of a. And for a discrete, if you want to include the a, then it would have just been f of b minus f of a plus the extra point when x equals a. But for a continuous random variable, the probability that x equals any value, any single value, is 0. So that means for a continuous random variable, both of these give you the same result. Namely, the probability that a less than or equal to x less than or equal to b is just f of b minus f of a. It's not true in the discrete case. In the discrete case, you have this extra number. So you got to be a little bit careful. Okay, so Let's make some observations so far. So again, what do we know? We have a probability density function. We know the probability. We know that this is always greater than or equal to 0. We know that the total integral from minus infinity to infinity of this function is called the normalization condition is 1. The probability that x lies between a and b is just the integral from a to b of f of x dx, or if you like, f of t dt. Okay. By the way, notice for this, so here's continuous. I have the table reversed in the text. So notice for a discrete random variable, we have this condition, and the corresponding condition is the sum of the probability of all the x of i's over all possible i's equals 1. Okay. F of x is equal to the probability that x is less than or equal to x, and that's just equal to the integral from minus infinity to x of f of t dt. In this case, f of x is equal to the summation of all little x less than or equal to x of p of x of I. So there's clearly an analogy between all of these. And by the way, I give a nice table on page 125 in the text. You might want to look at that. Remember, in the discrete case, for discrete random variable, we found E of x is a summation of x of I, P of x equal x of I, over all possible x of I. Well, we now give the following definition for a continuous random variable. If x is a continuous random variable, we define when it exists E of x to be the integral from minus infinity to infinity of x f of x dx. Or if you like, t f of t dt. Doesn't make a difference. So I can define the expected value, and more generally, I'm going to have Lotus. Remember Lotus, the law of the unconscious statistician. E of g of x is equal to the integral from minus infinity to infinity of g of x times f of x dx. Notice what follows immediately, since the integral is has linearity. Notice that E of c will again be c of E of x, and E of b, if b is a constant, is equal to b. That's because, to see that, notice this is equal to the integral from minus infinity to infinity of b f of x dx. Take out the b because it's a constant. And And then, of course, the area under the total curve has to be 1. So this gives you B. We define the variance exactly as before. And by the way, again, sometimes we will call this mu or mu sub x. Which is easy to show, and I will leave it as an exercise for you to show that this is equal to e of x squared again, minus e of x quantity squared. And by the way, the definitions make a lot of sense, because remember, from your calculus days, an integral, let me remind you of this one fact, to show you that all this really makes a lot of sense. An integral, say an integral like this, from a to b, of f of t dt, in calculus was defined to be something like this. The limit, say as n goes to infinity, of the sum of k going from, say, 1 to n, of f of c sub k times some delta x, where delta x was b minus a over n. Remember, these were called Riemann sums. So what's happening is when I'm looking at expected value, in the discrete case, an expected value had an x, has, say, another term in here, which we put in here. In the limit, it's going to give you the exact same result. So it's going to give you an integral. So you could actually think of the continuous random variable from a discrete point of view, write them as Riemann sums, and then take the limit as n goes to infinity, and these Riemann sums all become integrals. So, okay. So we have the only new thing here then is for a continuous random variable, e of x, or in fact, x to any power k, is equal to the integral from minus infinity to infinity of x to the k f of x, dx. So if you look at the example we did a minute ago, what was it? It was 1/8 x from 0 to 4. Did I remember that right? And 0 elsewhere. If I want to find, so here's my random variable, here's my density function. So e of x, the integral from minus infinity to infinity of x, f of x, dx. Notice this integral, this function is only defined between 0 and 4. So this just reduces to 0 everywhere else, from 0 to 4 of x times 1/8 x dx, or the integral from 0 to 4 of 1/8 x squared dx, which gives me x cubed over 24 from 0 to 4, which gives me 64 over 24. 8 goes 8, 8 goes 3. So e of x is 8/3. In the same way, e of x squared would turn out to be the integral from 0 to 4 of x squared times 1/8 x dx. This, of course, is x cubed over 8. If I integrate this, I get x to the 4th over 32 between 0 and 4. This gives me 4 to the 4th, which is over 32. 4 times 4 cubed over 32. 8. 64 over 8. This is 8 if I do this right. And therefore the variance is 8 minus 8 over 3 squared, or 8 minus 64 over 9, 72, what's it, 8/9? Okay. And sigma then would be the square root of 8/9. So the variance comes over very nicely as well, and so does the mean. The last notion I want to talk about is the moment generating function. So remember, the moment generating function is defined to be e to the tx. So for a continuous random variable, this would just turn out to be the integral from minus infinity to infinity of e to the tx times f of x dx. And here, in some cases, the integration may be a little bit messy if we needed to do it. But it's when I need it, it'll turn out to be very nice. Okay, so I want to talk about now two very special distributions. You'll see where I'll need the moment generating function, especially when I get to the normal distribution. So some special continuous distributions. The first one I want to consider is the uniform distribution. So let's suppose, let's think out of the box a second. F of x is a constant between A and B. So essentially that means every point is just as likely as every other point to occur. For example, suppose I know a bus comes arbitrarily between 1 o'clock and 2 o'clock. So the probability that the bus comes at over any particular interval, subinterval of that time, is going to be the same. So let's suppose this value is C. That means f of x is a constant. Well, I got to show you what this is going to be then. That means I know the area under this curve must be 1. The area under this curve is a minus b times c, and that needs to be 1. So c must be 1 over b minus a over this interval. So in fact, I have the following. The PDF is the following. It's equal to 1 over b minus a if x is between a and b, and it's 0 elsewhere. What about f of x? Well, firstly, just let me draw the graph again. So my graph looks like the following. It's 0 up until here. Between here and here, it's 1 over b minus a, and then it's 0. So if I want to compute the CDF, it's 0 for all x less than a. If x is any number between a and b, it's the integral from a to x of 1 over b minus a dx. And afterwards, it's going to be, when I get here, at least because I know the total area is 1, well, let's compute this meanwhile. This will just turn out to be x minus a over b minus a. If you compute that, when it's b, we get 1. So x greater than or equal to b, it's 1. So if you draw a picture of this CDF, by the way, it's here, and then it's linear up to here, and then where it's 1, at b it's 1, and then it's like this. Notice the CDF is always for a continuous random variable, it's a continuous function. In fact, some books define a continuous random variable as one whose CDF is equal to a continuous function. Okay, now for this random variable, here's why it's called uniform. What's the probability that x lies between C and D, where Here's A, here's B, here's C, and here's D. Well, I know f of x from A to B looks like this, right? So the probability lies between C and D is this area. What is the area? And by the way, this height is 1 over B minus A, right? That's what we showed. F of x is a constant. F of x is 1 over B minus A. So the area of this little rectangle, which is this probability, is just the length, which is D minus C, over times the height, which is 1 over B minus A. So the area of this rectangle, there's a probability that x lies between C and D, is just the area, this given area, which essentially says for a uniform continuous distribution, the probability that x is on some interval is equal to the length of that interval divided by the length of the total interval. That's sort of like a basic probability. So suppose I tell you Joe arrives randomly between 2 and 2:15 p.m. Determine the probability he arrives between 2:09 and 2:13. Well, this is clearly a uniform distribution. The total interval has length 15 minutes, right? The length of the interval that you're inquiring about from 2:09 to 2:13 is what? 4 minutes? So the required probability is 4 out of 15. Interesting result. Okay, so let's suppose I have a uniform distribution between A and B. And by the way, sometimes I put in the equal sign, sometimes I don't, it won't make a difference. What is the mean? Well, the mean is just x times f of x. So in this case, it'll be, I'll take out the constant 1 over b minus a, the integral from a to b of x dx, which gives me 1 over b minus a times x squared over 2 between a and b. So e of x is equal to 1 over 2 times b minus a times b squared minus a squared. I'm doing the calculus for you. 1 over 2 times b minus a times b minus a times b plus a, simple factoring. We have a cancellation here, and we find, not surprisingly, that the expected value of a uniform distribution is at the midpoint of the interval. That's cool. Now, what about e of x squared? Well, that would just be x squared times 1 over b minus a. And that gives me 1 over b minus a, x cubed over 3 from a to b, which gives me b cubed minus a cubed over 3 times b minus a. Do I do this calculation for you in the text? Somewhere I think I do. And if you do, by the way, notice this is the difference of 2 cubes. So you write this as b minus a times b squared. Was it plus ab plus a b squared? I'm trying to remember what it is. Plus ab plus a squared. Plus a squared over 3 times b minus a. You notice there's a cancellation. And then if you compute e of x squared minus e of x squared to get the variance, I do the calculation for you. It turns out to be b minus a squared over 12. So notice the variance for the uniform is equal to the length of the interval squared over 12. That's a pretty important result. And by the way, don't memorize it. It's going to be in a table that I give to you anyway. Okay, and I want to talk about just one other thing here, and then we'll be done. I want to talk about the exponential distribution. Okay. So, let me just, I got to use a notation from the text. X is said to be randomly, it's said to be an exponential distribution with parameter, do I call it A or alpha in the text? A greater than 0 if f of x equals ae to the minus ax for x greater than or equal to 0 and 0 otherwise. Okay, this is the exponential distribution. So the graph, when x is 0, it's A, it's 0 everywhere else, and then it goes off asymptotically like so. So the first thing to observe is f of x is equal to the integral from 0 to x of a e to the minus ax dx, or a e to the minus ax over minus a from 0 to x, and that gives me minus e to the minus ax from 0 to x. So f of x is equal to minus e to the minus ax minus 1, or we like to write it as f of x is equal to 1 minus e to the minus ax, okay, for x greater than 0. Okay, and so that's the CDF for the exponential distribution. And of course, it's 0 elsewhere. I didn't write that in. This is a useful result, by the way, as you'll see. Now, I could find the mean and the variance of the exponential distribution. It turns out that the easiest way of doing this is by how's my time? Oh, I got enough. Okay, I have enough time. Let's look at the moment generating function here. That will just be the integral from 0 to infinity of e to the tx times ae to the minus ax dx. Okay? Now, let's observe. I can write this as a integral from 0 to infinity of e to the, I'll write it this way, minus a minus t x dx. This is equal to a e to the minus a minus t x over minus a minus t from 0 to infinity. And by the way, I'm assuming a is greater than t here, and you'll see why I'm doing that in a minute. So this will give me a over, I'll put this minus sign here, a minus t, and this will give me e to the minus a minus t infinity minus 1. Something is bothering me. When x is 0, well, I'm trying to find my error here. Hold on, let me just clear this up a little bit. Let me just rewrite this as this is equal to a. Let me distribute the minus sign over t minus a. And then I have e to the minus a minus t from 0 to infinity. Okay, we're good now. So this gives me a over t minus a. If a is greater than t, then this is positive, so I have a minus infinity here. Minus 1. E to the minus infinity is 1 over e to the infinity, so 1 over e to the infinity, 1 over infinity is 0. So this just gives me a over t minus a, or I prefer to write it as with a minus sign, or a over a minus t. Okay, so I found, doing a little bit of integration, that the moment generating function is a to the minus t. I'll write it this way for a second. I do it this way so that the first derivative is easy to get. Bring down the power, decrease the power by 1, multiply times the derivative of the inside. This gives me a over a minus t squared. If I set t equal to 0, I get m prime of 0 is 1 over a. That's our mean. If I take the second derivative, I get 2a minus t to the minus 3 times minus 1. The second derivative at 0 turns out to be t is 0 minus 2a over a cubed. I'm off by a minus sign, so it should be plus. and you find out that the variance will just turn out to be 1 over a squared. So let me summarize. So for the exponential distribution, the mean is 1 over the parameter a. The variance is 1 over a squared. I will do some problems with this for you the next time we meet, and I'll do a little bit more about the exponential function. I'm not quite done with it just yet. I want to do some summary of it, but this is a good place to stop. Please do the homework exercises in section 3.1, and I'll talk more about this on Monday. Let me wish all of you a happy Thanksgiving. Anybody have any questions they'd like to ask? This is probably the time to do it.
I'm here, Professor. I came in late.
1 minute. Let me just get here. Okay. And who am I talking to?
Run.
Who's that? Shimron? Okay, Shimron. Let me just fix the roll.
Bye, Professor. Happy Thanksgiving. We'll see you later.
Okay, Evan. Have a nice weekend, everybody. Let me check the chat. Let me stop recording.